Hello everyone. In this video, I will give you a clear description about the factors affecting capacitance of a capacitor. What's a capacitor? A capacitor is a device that stores electrical energy in the form of charge. A capacitor can be made of different materials. In this video, we will see capacitors made from two parallel metal plates. These are the two parallel metal plates separated by a distance d. These metal plates are neutral before they are being connected to a battery. Neutral means the number of positive and negative charges are equal. Neutral, and in this plate it is also neutral. Positive, negative, positive, negative, positive, negative, positive, positive, negative. Let's connect these two plates to a battery. This is a battery, and this one is the lower potential denoted as negative, and this one is the higher potential denoted as positive. When these two plates are connected to the battery attracts electrons from the plate connected to the positive terminal and pumps into the plate connected to the negative terminal, like this. Electrons are transferred by the battery, attracted by the positive terminal and pumped to the plate connected to the negative terminal. Now we have one positive, and we have one negative, clear? It continues transporting these electrons from the plate connected to the positive terminal to the plate connected to the negative terminal, like this. Like this. Like this. No. Now look. Positive charges are stored here. Positive charges are stored here. And negative charges are stored here. The number of electrons, 1, 2, 3, is equal to the number of positive charges here on the left side, 1, 2, 3. Therefore, we say this is plus Q, this is plus Q, and this one is minus Q. The positive and the negative charges are equal in magnitude, and potential difference is produced between these two plates because of the positive and the negative charge in the direction of this. This is electric field, and don't forget electric field is equal to, or voltage is equal to, electric field times distance between plates. This is the electric field which is directed from the positive to the negative, and voltage is developed between the two plates. This is the voltage between the two plates, V. We have two voltages. This is V0, which is source voltage, clear? As charging continues, or charge transfer from the positive plate to the negative plate continues, the charge stored increases. As charge stored increases, the voltage between the plates also increases. As charge increases, the voltage between the plates also increases. As charge increases, let's use a symbol, an arrow, upward arrow, that means increase. As charge increases, the voltage between the plates also increases. As charge doubles, the voltage also doubles. This relation is directly proportional. Charge is directly proportional to voltage. Charge stored in the capacitor is directly proportional to the voltage between the plates, clear? Therefore, their ratio is constant. This implies charge over voltage is constant. This constant is denoted by C and called capacitance. Q over V is equal to C. This implies Q is equal to what? CV. Q is equal to CV. Charge and voltage have a linear relation. Let me give you a quick quiz to understand this. True, false. True, false. Question. The given area of the plate is constant and the distance between the plates is also constant. Keeping the area and the distance constant, answer the following questions by writing true and false. You can pause the video to answer the questions. 1. As charge increases, capacitance increases. 2. As charge increases, capacitance decreases. 3. As voltage increases, capacitance increases. 4. As voltage increases, capacitance decreases. Can you identify the false and the true relations in these 4 statements? What can I say about number 1? Number 1, as charge increases, capacitance increases. Now we have a good analog in water flow, or when water is stored in a container. You can assign the water as the amount of charge. The container that the water can be stored is the capacitor, and the level of the water in the container as the voltage or the potential difference between plates. Let me repeat it again. Assign the water as the amount of charge. The container that stores the water is the capacitor, and the level of the water in the container is analogous to what? The voltage between the plates. Question number 1, as charge increases, capacitance increases. That means when we increase the amount of charge stored in the capacitor, the ability of the capacitor to store charge also increases. That means as you increase the amount of water in a container, in a given container, having a fixed volume, the capacitance or the ability of that container to store water increases. That is false. Because if you have a 20-liter container, when it has no water, its ability to store is still 20 liters. And when it is half filled, its ability to store is still 20 liters. And when it is totally filled with water, its ability to store is 20 liters. Therefore, the amount of that container or the ability of that container to store water is independent of the amount of water in the container. The same is true here. Capacitance of a capacitor is independent of the charge stored in the capacitor. Therefore, this is false. False. Capacitance is independent of charge. This one is also false. When the charge stored increases, capacitance remains constant. It does not decrease. Number 3, as voltage between plates increases, capacitance increases. It is false. Capacitance does not increase when the amount of voltage between the plates increases or decreases. Therefore, these 2 are false. False, false. Let's go back to our analog. Question number 3. As voltage increases, capacitance increases means as the level of water in the container, 20-liter container increases. As the level of water in the 20-liter container increases, the ability of that 20-liter container also increases. That is nonsense. It does not give sense. Therefore, the capacity of the container is independent of the level of water in the container. The same is true here. The capacity of the capacitor to store charge is independent of the amount of charge between the amount of voltage between the two plates. What's our conclusion? Our conclusion is charge and voltage are not factors affecting capacitance. Conclusion. Charge and voltage are this voltage is the voltage between plates. Charge and voltage are not factors affecting capacitance of a capacitor. In other words, capacitance of a capacitor is independent of the charge stored in the capacitor and the voltage between the plates of the capacitor. Capacitance of a capacitor is independent of the charge stored and the voltage between plates. The voltage between plates of the capacitor. Clear? Now, what are the factors affecting capacitance of the capacitor? What are the factors affecting capacitance of a capacitor? Capacitance of a capacitor. Okay, let's see. One is area of plates. That is A. As you increase the area from this to this, its ability to store charge increases. C1 and this one is C2. Therefore, a lot of charge stored here because it has so many spaces to store charge. And this one will have limited amount of places for charge storage. Therefore, one factor is area. As area increases, as area doubles, area A doubles, capacitance also doubles. Capacitance C also doubles. Now let's write the relation. Capacitance is directly proportional to area of the plates. This is one relation. The second factor is distance between plates. Distance D between plates. That means, let's draw the two plates again to illustrate this. This is the distance between the plates D. As you increase the distance between the plates like this, the capacitance decreases. Because voltage, as the distance between the plates increases, the voltage between the plates increases, keeping the charge constant. Now capacitance decreases when we make the two plates closer to each other. Capacitance increases. As D doubles, as D or distance between plates doubles, capacitance decreases by a factor of 2. This relation is called inversely proportional. Capacitance is inversely proportional to D. When we bring the two relations together, we will get capacitance is proportional to area and inversely proportional to D. Let's crisscross. This is over 1, and when you crisscross, CD over A is constant. This constant is epsilon naught. This is the permittivity of free space, and epsilon naught is a constant. CD over A is equal to epsilon naught. Can you make C the subject? Yeah. C is equal to epsilon naught A over D. This is capacitance of a capacitor when there is no dielectric. Therefore, we had better say C naught. C naught. C naught means capacitance without dielectric. We are going to see what a dielectric is. Epsilon naught is 8.85 times 10 to the power of minus 12 Coulomb squared per Newton meter squared. What's the third factor? We can take a dielectric as a third factor. Before that, let's describe what a dielectric is. Dielectrics are materials inserted between plates of a capacitor. Materials, non-conducting materials. Dielectrics are non-conductor materials. Non-conductor materials like paper inserted between plates of a capacitor, for two purposes. One, to prevent the two plates, since they carry opposite charges, the two plates from being discharged. If they are made contact, they will be discharged. Positive and negative will be joined, and we will lose our energy, the energy stored in the capacitor. The second advantage of this capacitor is to increase capacitance. How a dielectric increases capacitance? Let's take 2 or 3 minutes how a capacitor or a dielectric increases capacitance in the capacitor. Let's draw the two plates. Assume these are the two plates. And let me feel a dielectric. No, excuse me. Between these two plates, assume this is a dielectric inserted between the plates. It might be mica, paper, or paraffin. This yellow pigment is considered as dielectric, and this is the distance between the plates or the thickness of the dielectric. We have this positive plate and we have this negative plate. 1 2 3 4 5 6 1 2 3 4 5 6. The number of positive and negative plates should be equal, and the electric field is this one. This is the electric field. Without dielectric, E naught, and when the dielectric is inserted, its charges will be polarized. The charges of the dielectric will be polarized like this. The negative will be on this side, and the positive will be on this side. The negative will be on this side, and the positive will be on this side. Clear? The negative will be on this side, and the positive will be on this side. This is called polarization. The dielectric, even if it is a non-conductor, it is positive and negative charges will be switched like this. This is called polarization. And a little electric field which is opposite to the field without dielectric is created. This is electric field with dielectric, clear? Opposite to the external electric field. What's the net electric field? The net electric field is E net. The net electric field or the total electric field is equal to this E naught, the external electric field or the electric field without dielectric, minus this electric field of the dielectric, this electric field of the dielectric. Okay. Now you understand that when dielectric is inserted, the dielectric itself produces a little electric field which is opposite to the external electric field. As a result, this electric field decreases. Inserting dielectric will decrease electric field. Inserting dielectric will decrease electric field. You know, V is equal to ED. When this electric field decreases, when E decreases, the voltage also decreases. Now capacitance with dielectric, without dielectric is equal to charge over voltage without dielectric. And capacitance with dielectric C is equal to charge over voltage with dielectric. Charge with dielectric and without dielectric is the same, because whether you insert the dielectric or not, the charge remains constant. Now let's take the ratio. Capacitance with dielectric over capacitance without dielectric is equal to Q over V naught divided by Q over V. This V is capacitance with dielectric. You cancel Q by Q and take this V to this side. Is equal to V over V naught. But V is less than V naught. Don't forget, V is less than V naught. Therefore, this ratio is less than 1. C over C naught is less than 1. This implies C is less than C naught. That means capacitance, no. Okay, I made a mistake, excuse me. Okay, Q over V here. Q over V naught over V naught. This is Q over V. C means C over C naught means is equal to Q over V divided by Q over V naught. Q cancelled by Q is equal to, you take this V naught over V and V naught is greater than V. Clear? Therefore, C over C naught is equal to V naught over V is greater than 1, because V naught is greater than V. This implies C is greater than C naught. This is a good relation. C is greater than C naught means capacitance with dielectric is greater than capacitance with dielectric. C is greater than C naught means capacitance with dielectric is greater than capacitance without dielectric. Capacitance without dielectric. Now C over C naught is equal to V naught over V is equal to E naught over E. E naught means electric field without dielectric and E means electric field with dielectric. V naught is voltage without dielectric and V is voltage without dielectric is equal to constant. This constant is K, and K is called dielectric constant. Dielectric constant. K is dielectric constant. The ratio of capacitance with dielectric to capacitance without dielectric is the same as the ratio of voltage without dielectric to voltage with dielectric is the same as the ratio of electric field with no dielectric over to voltage electric field without dielectric. K for every dielectric material is greater than 1. K is equal to 1 for air or vacuum. Now let's take C naught is equal to epsilon naught or A over D. Now you remember this relation. Take this relation here. C over C naught is equal to K, and this implies C is equal to K times C naught. What is C naught? C naught is epsilon naught A over D. Now capacitance is equal to K epsilon naught A over D. We can consider this as a third factor. What are the factors? Area of the plates, distance between the plates. Capacitance is directly proportional to the area of the plates, and capacitance is inversely proportional to the distance between the plates. And the third relation is using a capacitor with larger dielectric constant will increase capacitance. Now we have three factors that affect capacitance of a capacitor. One is area of the plates, the other is the distance between the plates, and the other case is inserting a dielectric, having larger dielectric constant to increase the capacitance. These are the factors affecting capacitance of a capacitor. Now capacitance depends on geometrical factors. Capacitance of a capacitor, capacitance of a capacitor depends on geometrical factors like area of the plates and distance between the plates. It stands for capacitance. It is independent of the charge stored and the voltage between plates. Thanks for watching. If you liked the video, please subscribe to get more videos. Goodbye.